And I'm waiting your questions. Yes.
Talking about questions from like unit one.
Mm-hmm.
At the bottom of part A, it's talking about construct the 16th complement of the hexadecimal number 3d4.
Okay.
I didn't really understand what that meant.
Okay. So construct the, did you understand the tens complement or not that either?
Yeah, no, I got that one, but I didn't get this one.
Okay. I'm going to change it, so I'm not doing it for you. I'll do something like it. I'll do a different number. So I'll do 2 and B and 7. Okay, 2B7. That's not a 7, that's a 7. Okay. So that's what I was asked to do, the 16's complement. Let me make it a little bigger or there. Okay, so we have this idea that we went over in more detail about the 2's complement. And then we had a process for that, exchange 1s and 0s and add a 1 to the 1s place. But the whole idea was to construct 2 numbers that if I had some base, in that case binary, base 2, and a finite number of digits, that if I added the 2 numbers, I would end up with zeros. And that's, I want to do that in this case, but I want to get 16. I want to get 16s. I want to use 16s instead of 2s. I'm going to insert a row above. Okay. So in this first place, in this 1's place, I have a 7, and I ask, what do I add to 7 in order to get a 0 in this first place? And you're not allowed to say -7.
3?
3 if it were the 10's complement.
Oh.
But it's the 16's complement. So it is 8 would be 15, and I need it to be 16 because that's my base. So I need a 9. So 7 and 9 will give me 16, which is my base. So that is 0, carry a 1. A is 10, so B is 11, 12, and
4.
I need a 4.
Last but not least, you need a.
So I have 3, so I need what? Just tell me in decimal what I need.
13.
Would, yes.
B, sorry, 11, 12, 13, 2.
A is 10, B is.
Sorry, A, 10, 11, 12, 13, B.
Okay. Now let's check. I like to check. And then there would be a carry blah here, which would be here if you want, but you don't need to do that because it's not there. It's only a 3 digit hexadecimal number. It's essential that we are working with a finite system. That is. Okay, so let's check it. Calculator. Not scientific, but programmer mode. And we are in hex. And we want to check our answer here. So is 2B7 plus D49 equal to 1000, and we're interested in the 000. Okay. So now tell me how to cheat. Yeah, well, I checked with the calculator. Now tell me how to cheat with the calculator. Exactly.
So, Professor, is there any reason why you don't care about that one?
Don't care about, because it's a finite system. So the whole concept of 2's complement, 10's complement, 16's complement, whatever, is based on the idea that we have only so many digits in a representation, so that we can use our normal addition and end up, but in this finite system, all the ones that are really there are zeros. And then there's this extra one that we used to call overflow, but we're not going to call it overflow now. But since the part that's there and we care about is 0, we're going to say that D49 is really the negative of 2B7, or at least it's possible for us to interpret it that way if these are signed hexadecimal numbers.
Gotcha.
And then he told me a cheat, did he not? Yes. He's a good cheater. So in hexadecimal, if you just turn it around. Right, so easy, and I like to cheat too. So that was, and you could play, if we were in decimal mode, we can get the 10's complement. If we were in binary mode, we could play the game to get the 2's complement, but we know another method for the 2's complement. Exchange 1s and 0s and add a 1. So now you have to do a different number, but I told you how to do it and also how to cheat, so it should be, you should get it. I told you, just ask, I'll tell you everything, just ask. What else are you going to ask me?
At the bottom of the part B of the lab, it talks about the ID.
Okay,
I think how do you figure out like how many hexadecimal characters you can use?
okay, let me catch up with you here. So it was 1B. Bridge width, the bottom again. Okay, so it's the IP or the physical?
This is how many hexadecimal characters.
So, okay, so that's in the physical. So one time,
You were just want the B, C, E, F, D count, or are you trying to figure out, are we trying to figure out how many?
this like throws people sometimes. The 9 in that example up there is a hexadecimal digit. The hexadecimal digits are 0 through 9 and A through F. So it's not asking which one of these are hexadecimal but not decimal. That's not the question. The question is, how many hexadecimal digits are there? Well, they're all hexadecimal digits.
So 12.
So 12, yes. 1, 2, 3, 4, 5, 6, yes, 12.
So typical MAC address, got it, all right.
Yes. That is a MAC address. And when you have hexadecimal digits, some hexadecimal digits are 0 through 9. So it is 12. So how many bits is that? 48, because there are 4 bits in a hexadecimal. So I can't do any fun change the number here. I could change these numbers, but doesn't change the answer to any of the questions. And if there are 12 hexadecimal digits, or correspondingly 48 bits, then how many combinations are there? And I don't want, oh, there are reserved ones and blah, blah, blah. I don't care about that. 2 to the 48 power. What's the other answer? That better be the same. 16 to the 12. So there were 16 possibilities for the 12 digits. There were 2 possibilities for the 48 digits. And that really should just be the same counting. So,
Keeping with that same sheet, I was having a bit of an issue with the fractions, 6 point.
okay, I'm just confirming that 2 raised to the 48 is 281, yada, yada, yada. And then 16 raised to the 12 is 281, yada, yada, yada. Okay, so they were the same, so that's good. Now, what am I doing?
As I'm moving back to the fractions. the
Fractions.
Point binary with decimal, so I was having-
This one here?
yes, sir.
Okay. All right, so it's the fraction part you don't like, presumably?
Yeah,
Okay. So for the whole number part, let me go back to programmer. Which one? Oh, let me make up a completely
Yeah.
different one.
even the one you have there.
Insert row below. Too many. All right, there we go. So I want 98. I'll do 98, then I'll do 1. I'll do 2. I don't know, I'm going for punishment. And I'll do 247 again. So I don't have to do that part again, but I want something 1, 2 like that. Okay. All right, so 247 is just a decimal number, whole number, and I'm getting the binary. It's less than 256, so it only takes up 8 bits, but I asked for 16 bits. So if you're giving me the careful answer, you will give me the 8 leading zeros.
You mentioned that, okay, yep, that's, all right. Thank you. Okay.
I probably wouldn't take off points for that, probably not, for a 1/10 of a point or something if I were really being picky. Okay,
Thank you.
but now for the fraction, okay. So you can do the game of 0.98 and multiply it by 2 and get the whatever you get, 1 point something, and take that 1 and do that 8 times because there are 8 bits, but I don't want to do that because, as I say, I like to cheat. Okay, so if I were playing that game of the 0.98, the algorithm that we first wrote down was 0.98, and we multiplied it by 2, and we got 1.96, I guess. I don't know, 1 point, pretend I know how to multiply. And I take that one, and that's the first one after the dot, and then I would take the 0.96 and multiply that by 2. And what's that? I'm already tired. Okay. So, what does that algorithm tell me to do? It tells me to multiply by 2, and I would multiply by 2 8 times because I wanted 8 bits. So multiplying by 2 8 times is multiplying by 2 raised to the 8th. Right?
Yep.
Right. So I'm going to go over to scientific mode where I can do that. I'm going to go 0.98 times 2 raised to the 8. Take my fraction, multiply it by 2 raised to the number of bits that I requested. 250.88. I'm going to, can I remember? Maybe I can. 250. Or I can just do this. And now I want to, so I'm just going to truncate. Some people will round. If you're different from me in the last bits, okay, I'll say you round and I truncated. I'm going to truncate. I'm going to take my 250. I'm going to go back over to programmer mode. I'm going to put in the 250, Control V, I guess it is. And then down here are my 8 bits in binary.
So it would be the first 3 decimal points and then a period last.
So all 8 bits in this case, I was expecting 8 bits. I got 8 bits, and they are all they're all part of my fraction here. So this was the halves place. So there's a half and a quarter and an eighth and a 16th and a 32nd, but no 64ths, something like that. Is that okay?
Yeah, that's great, thank you.
So now I'll do the 0.12. Because that brings up just one distinction. So I'm going to go back to scientific mode. And I'm going to put in my 0.12. And I'm also representing it with 8 bits. So times 2 raised to the 8. And now I get 30.72. So all I want is 30. I'm going to go back over to programmer mode. Paste in my 30, and here's my binary for 30. Now, when I put it into binary mode so then I can copy, it threw away 3 of my bits because it doesn't show leading zeros. But I need them. I asked for 8 bits, I better get 8 bits. With a different font size, apparently. So that you need those zeros, and those zeros make sense. The first 0 is the halves place, 0.12 is less than a half. The next one is the quarters place, 0.12 is less than a quarter. The next one is the eighths place, 0.12 is less than an eighth. An eighth is 0.125. And then the ones start coming in. Is that all right? Questions?
At the top of part B, this is with the calculator, how many bits is used to represent binary numbers?
This
The calculator.
of the calculator here. Okay. Oh, the calculator. Okay. So the easy way to answer the question is to put in a 1 negative. Because that's all ones. And then here they are, grouped in 4s. So I'll count the groups of 4 because I'm lazy or smart or both. I don't know. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 4s, 64. So it uses 64 bits. And what's the largest number it can represent? Well, I just put in a -1 to figure that out. So we know that it's signed numbers and it's representing. So what's our formula there? Half of them are positive, half of them are negative. So it's 2 to the 63 minus 1. Okay, so I have 2 to the 64 combinations. I divide it in half, so half are positive, half are negative. And then I want 0. I love 0, and I steal from the positives. So that's 2 to the 63, and I subtract 1, so then I have the 0. And that ought to be 1 followed by zeros if there's any justice in the world. So let's see what 2 raised to the 63 minus 1 is, and that's not 2 to the 62, that's 2 to the we know our order of precedence of that powers come before subtraction. So you do the 2 to the 63 and then you subtract the 1. And here's this big long number, okay. And let's go back over to our programmer mode and paste it in there. Control V. And oh, what did I say? That it was 1. Oh, that's right. This is the big number. Sorry, I'm being stupid. The 10000 was the most negative number. This is the most positive number, which is 0 and all ones. And so the magnitude of the largest negative number is 1 more. You can always get 1 more negative number because we stole from the positives to get 0. So there's always the magnitude of the most negative number is 1 more than the magnitude of the most positive number. Questions? Everybody's acing lab 1. Is that right? Yes. Good.
I mean, I didn't. Me personally, I didn't do the part C because I didn't know how to get the program on my computer.
Okay.
So I don't know.
Well, you'll do it here tonight and get it done and get it in. And
Okay.
that's not a big deal. I haven't even, I'll probably make it, I might make both of these things due next week, or maybe I'll make part A or something of this lab due next week and sort of start staggering or something like
Very
that.
good.
But that's not a problem. I've got to find out from IT whether it can be downloaded by Google.
But you only get like a 45 day trial on it.
That's perfect.
What?
Yeah, so
45? 45 is a month and a half.
I'll
or
sign up with a different email.
Oh, cheap system. Okay. So, if you can, if there's like, if we have a student version, I will certainly let you know. There's a student version for some amount of time. And I've seen people find online version somewhere. They usually end up with like a slightly older version. And if you end up with a slightly older version, you just have to be careful that once you touch an old file with a new system, say you made it on, say you found an old version, you put it on your computer, all was good and fine, and then you ran that file here in this lab, then it would become version, I don't know, whatever it is, 14 or something like that. And there's like no going back. There's no like save as an old version. They used to, but they don't have it anymore. So you just have to watch version control. Good lesson to learn in computer science anyway. But all the numbery things were doable. That's part of the reason for breaking the lab in pieces, so that one piece isn't hanging on the others. Okay. So I will get in touch with IT, they've been kind of nuts for these first 2 weeks, but I will try to get in touch with them and see if it is downloadable. If not, you'll ask your classmate how he found at least the 45-day version. All right. Any other questions, Unit 1? Okay, sounds good. All right, so I will do the lecture part of Unit 2. So there were the pre-recordeds for lab or for Unit 1. There's the homework, there's the slideshow, there's the 3 parts of the lab. Here's the recorded demo of the multi-sim. Okay. Here's the pre-recorded, the homework, the 3 parts of the lab. Here's some more pre-recorded stuff. Here's the PowerPoint. Apparently a very old PowerPoint because it's PPT and not PPTX. Slideshow from beginning. Let's go with that. Okay. So we're going to do again sort of like 2 halves. It's only like 60-70% of the way through the class before these sort of 2 things merge. So we'll do something with resistors, a physical thing, and we'll do a logical thing. Okay, we'll start with the logical thing. So there is sort of like logic in philosophy, there's logic in math. We're going to be doing digital electronics, a physical representation of logic. So there are different vocabularies floating around depending on whether you're a philosopher, a mathematician, a computer scientist, or a physicist, doing an electronics class. So there are, we'll talk about Booleans. If you're a computer scientist, you'll talk about Booleans. If you are doing logic, you'll talk about logical statements, things that can be true or false. In programs, we often talk about conditions. Conditions are things that can be true or false. In electronics, we will have inputs and outputs, and they will be high and low. So just whether some quantity is high or low will correspond, we'll say is going to correspond to true and false. So we'll talk about ones and zeros. We will talk about true and false. We will talk about high and low. We will do so fairly interchangeably. And we will almost always work with the convention that high is true is 1. That doesn't have to be. You don't have to interpret that way. You could interpret high as false or something like that. That you could do that, but we will sort of stick almost the whole time to the consistent interpretation of high is true is 1. Okay, so Boolean algebra is named after somebody named Boole, who it's been around. Boole didn't invent it. It was sort of Boolean stuff. You can find logic back in the philosophers, the Greek philosophers way back when, but he studied it sort of more systematically and extended it a bit, as mathematicians tend to do. Okay, so this is a joke. You're supposed to laugh. Okay. He laughed. Okay, 1. All right. So we have Boolean algebra. So I'm going to work with a notation. I'm not going to use the discrete math notation. It's hard to type, so I don't like it. And I also find it confusing. So I use the notation that is most like the notation for regular algebra. So I'm going to use a notation for my Boolean algebra that's a lot like my the way I write regular algebra, and I just have to remember that the only possible numbers are 0 and 1. Okay. And so in regular algebra, we have operators like addition and multiplication and so on, and we will have Boolean operators. And so our standard 3 are going to be and, or, and not. So if and is, we're going to put, let's say we have 2 things, we can have more, but let's say we have 2 inputs. And if they are both true, we get a true out of an and, otherwise we get false. And or is sort of the in a way the opposite, in that it's the only way with an or that we get a low is if we have 2 lows. So for and, I have to have 2 highs to get a high. With an or, I have to have 2 lows to get a low. And not is as a single input and gives you the opposite of whatever you put in. So you put in a high, you get a low, you put in a low, you get a high. Okay. And so here is the representation. I'm going to use the representation of A followed by a prime is going to be the inverse. There is a notation where you put a bar over the A. That's hard to type. There's a notation with a little sort of rectangular squiggly. The mathematicians love that. It's hard to type. I don't like things hard to type. When we make a circuit in electronic, or what are we calling it? Multisim. The symbol for a NOT gate is a triangle with a circle. The circle is important. The circle is the actual inversion. Anytime you see a little circle, that means inversion in these gates. A and B, we're going to represent by just A next to B. This is based on that Boolean ANDing is like multiplication in regular algebra. It's the Boolean version of multiplication. So I'm going to use the same symbols as multiplication. Mathematicians will invent some other symbol because you might confuse it. I'm going to say, all we do in this class is Boolean. If you confuse it, that's your fault. But in the context of this course, there's no confusion. All we do is Boolean. And so A times B means and. The or is a plus because or is sort of the Boolean equivalent of addition. And then there's a gate that is sort of comes up sometimes called the excluded or. So we'll have to write out the truth table for it so we see what it looks like. But you can, if you put it into words, it is one or the other, but not both. So it is, if A is high and B is low, you get a 1. If A is high and B is low, you get 1. If A is low and B is high, you get 1. But if they're both low, if they're both high, you get low. There's something called a NOR, which is just a combination of an or and a not. So you or them together and then you invert it. And there's something called a NAND, which you use an and then a not. So I'm presenting this, a NOR and a NAND, as if it's just a combination of 2 of more fundamental gates. When we finish the course, or when we get close to the finishing the course in week, I don't know, 8, 9, 10, somewhere in there, we're going to learn that physically, it's the other way around. Physically, NAND and NOR are more fundamental. They're the ones that we can make from transistors. So the way we're talking about it now, the way that's easiest for us to talk about as we're introducing them is and NOR are not are the basic building blocks, and we can build NOR or NAND from them. And physically, it's actually the opposite. So you don't have to understand that now, but I'm just fair warning that your whole world will be inverted at the end. Okay, so I use my not notation is the prime because it's the one that's easiest to type. Does it have to be straight? No. Just use the apostrophe that's right on the keyboard. Don't knock yourself out. Make it easy. There's a plus right on the keyboard, and you can put two letters right next to each other on the keyboard. So this was the keyboard friendly notation. Here are some of the other notations. If you use them, they are correct. I will not mark them wrong. I will secretly hate you. Maybe I'll publicly hate you, but I will not mark it wrong. But I'll probably have to look it up because I can never remember which one's the V, which one's this. And so still more vocabulary. We're going to call A and B inputs, and then they're going to produce outputs, but that's an electronic idea, inputs and outputs. In computer science, you refer to these high and low things, or these true and false things, as Boolean variables. If you were in a logic class, you'd call them proposition or maybe predicates. All just fancy terms for the same thing. These are all things that are high, low, true, false, 1, 0. Okay. The prime does not distribute. This is the one bad thing about the notation is people want to do something with it they can't do. The prime does not distribute. You cannot say or it distributes if you're smart and know how it distributes. That's a different way of thinking about it, but it doesn't distribute the simple way of A, B quantity prime is not A prime, B prime. So here's A and B. Here's all the possibilities for A and B. This is a truth table. 0, 0, 0, 1, 1, 0, 1, 1. That's all the possibilities for two inputs. I go in the opposite direction they do in discrete math. All you need to have is all the combinations, but my combinations make sense and theirs don't, because I use zeros and ones, and so I am counting 0, 1, 2, 3. They work with T's and F's, and I don't know. And they count backwards. I don't know why. All right, so here is A and B. Only when both A and B are do you get a 1, and then the inverse of that is 1, 1, 1, 0. Whereas over here, if I take A and invert it, 0, 0, 1, 1 of A becomes 1, 1, 0, 0. The 0, 1, 0, 1 of B becomes 1, 0, 1, 0. And if I AND that, only the first one is a 1. So these are not the same output. They're not the same truth table. Don't distribute the prime. Okay. So now I just showed you truth table, and now I'm going to tell you what a truth table is. Okay, that makes a lot of sense. Truth table is we have our things that we've identified as inputs, and we write out all the possible combinations of those inputs. I do it by counting, and then I know if I've counted up, if I had n inputs, if I count up to 2 to the n minus 1, I know I have all the possibilities. And if for each possible input I give the output, I have produced a truth table. And that means if I have a circuit, or if I have a scenario, if I understand all the possibilities for that scenario, then I understand the scenario. A million years ago, I had a student who would say, I don't understand. And then I would explain the truth table, and she would say, yes, I understand. I understand that, but I don't understand. And there was also a language barrier, I'll say. But but she would say like, but I don't understand this. And it's like, you do understand this. All there is the truth table. If you understand the truth table of a logic circuit, you understand the circuit. Unless you're an engineer and you have to worry about the power distribution or something like that, we're never going to do that. So if you understand the truth table in this class, you understand what we're doing. Okay. So we're going to take ones to be true to be high. We don't have to do that, but we will. And we have to take some physical quantity. Typically for us, it will be voltage. Early on, I will, in the first lab or two, I will emphasize this and I'll say, what are the voltages and are they high, or are they low, and are they true, or are they false? And then later on, it'll just be ones and zeros, and we'll just assume everybody gets it. But for a lab or two, I'll be, here's a voltmeter, measure the voltages. Is that high or low? That depends on the context. The context is usually decided by the battery. If you put in a battery that's 5 volts, then 5 volts is high. If you put in a battery that's 12 volts, then 12 volts is high. Okay. So when we're making the truth table, we make all the combinations. I make all my combinations by counting. So I start at 0 and count up to 2 to the n minus 1. All that really matters in a truth table is that you have all the possibilities. So I'm going to change this on you, probably next week, and produce a different order of a truth table. But in my sort of beginner truth tables, I put them in the counting order. Okay. Then, so what we want to learn today is how to write. So the truth table explains the scenario. If you understand, here are all the possible inputs. For each of those possible inputs, here's the output. Then if you can make a circuit that has those inputs, with those inputs lead to those outputs, then you have built that scenario. That's what we want to learn how to do. And we're going to work with ands, ors, and nots for now. Okay. So if we had 2 inputs and I'm going to start working with ands and nots, then we know that when we have an and, there's only one way to get a high output. That was something we said about a high. If you get 2 highs, then everything else is low for an and. But I'm also have some nots rolling around. So if I not both A and B, then these zeros turn into ones and I feed them into an AND gate and I get a 1. So the truth table for A prime, B prime has a 1 in the first row and 0 every place else. The truth table for A prime B has a 1 in the second row and 0 every place else. A B prime has a 1 in the third row and A B in the last row. Okay. So I can think of those as expressions for the rows. So I can think of A prime, B prime as an expression for that row. A prime B as an expression for that row, A B prime for the next row, A B for that final row. Okay. So here is one way to make an expression for a truth table. So here's just a scenario. I'm going to do it for this scenario. This is sometimes when people get confused that we do a truth table and then they think we've done all truth tables. We will do a method that will apply to all truth tables, but not all truth tables look like this. This is the truth table for a scenario. There are other scenarios. So this is the scenario where there are 3 inputs, A, B, and C, and we're going to do, our rules are going to be majority rules. So if I have 2 inputs or 3 inputs that are high, I'm going to be high. This is just the scenario. This is the scenario that I've chosen as my example. It's not the only possible scenario. The A, B, and C part is always the same. Those are just all the possibilities. But this part over here, the outputs, can be different for different scenarios. There are 8 outputs. The outputs can be high or low. So there are 2 to the 8 possible scenarios. This is one of them. So in our approach, we are going to take the outputs which are ones. So the ones were here, the 0, A was 0, B was 1, C was 1, and then the last 3. Those were the ones, those were the rows with an output of 1. I write my expression for my AND expression for each of those rows. So this was A prime B C, A B prime C, A B C prime A B C. If the input is 0, I invert it for my expression. If it's a 1, I do not. I'm working with AND gates, and I want all the things in the AND gate C's to be 1. And so if it's a 0, I invert it so that by the time it gets to the AND gate, it's a 1. So that 0 gets primed, and these 1s stay as they are. So this row here is A prime B C. That's the expression for that row. This one here, A101 is A B prime C. The B was a 0. Before I get it to the AND gate, I want to invert it so that all the things in the AND C's are 1s. So these are my expressions. I wrote down all the expressions, but I'm only interested in the expressions where the outputs were 1. So that's why I highlighted them in bright yellow. Apologize if you're colorblind. Okay. We're okay. We're okay. Nobody's shaking their head no, but nobody, he says yes, okay. All right. So I write my expression for this scenario by taking my AND expressions for the rows for which the output was a 1. So here, for that majority rules, here's my expression. A prime BC plus AB prime C plus ABC prime plus ABC. Is this the only possible expression? No, it doesn't work that way. There are other possible expressions. This is an expression. This is not the expression, it's an expression. The other expressions are going to be logically equivalent or wrong, but if they're the correct expression, they are going to be logically equivalent. They are going to produce the same output for the same input. They might not be electronically equivalent. They might be different engineering wise. They may be different. They may have different power requirements or something, but they will be logically equivalent. So this is an answer. It is a correct answer. It is only one of a number of correct answers. This is known as the sum of products. We're using our fundamental thing here was we were starting with and in the algebra that I use, and works like a product. If any of them are zeros, you get a 0. That's how a product works. If any of them are zeros, you get a 0. So the main thing was a product, and then we made a sum of them. So the whole thing is known as the sum of products. It's also known as a mini term. We will learn next week how to simplify. If you simplify a sum of products, you will probably still have a sum of products. But you will no longer have a min-term. Like, min-term means I did the basic thing, all the terms are there. Every row has all the input terms there. But if I don't ask you to simplify, you don't have to simplify. Okay. So people spend their time simplifying when I never ask them to. Okay. And okay, so I stole stuff from Wikipedia long ago. If I asked you to make this circuit, this is what it would look like. Okay. I have, there are easier versions than this, but this is the version I usually make because I'm a glutton for punishment. So here is a battery, and I have a wire coming out of the top and a wire coming out of the bottom, and the bottom is also connected to a ground. So this top is 5 volts and this bottom is 0 volts. So that is my high and my low. I have a switch. I have 3 switches, A, B, and C. On one side of the switch, there are 2 places it could connect, and then there's just one thing coming out of the switch on the other side. The switch, if I type an A on my keyboard, that switch A will flip back and forth. And so right now it's connected to the low, but if I hit the switch, it will connect to the high. You can also click on the switch. So I could type it and make it move back and forth. You could click on it, make it move back and forth. If you like the keyboard, you like mouse, your choice. So I can change whether A is high or low. Right now it's low. I can change whether B is high or low. Right now it's low. I can change whether C is high or low. Right now it's high. How do I know it's high? Because the way the switch is connected, it's connected up here to this upper wire. This upper wire is connected to the high end of the battery. So it's high. So it's 1. So it's true. So that's the switch part. Then I have A in my expression. So this wire that comes out of A corresponds to A. A could be high or A could be low, but this whole wire that's coming straight out of the switch corresponds to A. I peel off of the A and go through a NOT gate, a triangle with a little circle, and then this second wire corresponds to A prime. Whatever A was, I put it through a NOT gate, that's A prime. So I don't know whether A is high or low, depends on the state of the switch. But this first wire, whatever A was, this whole wire is A, and this, after the NOT gate, this whole wire is A prime. B, B prime, C, C prime. What I've done so far, what I've told you so far, is the generic part that is the same for all the scenarios. You are going to have to build one of these, and one of these is going to be on the first test. You can build these switches. You can have your battery, you can have your switches, you can have the NOT gates, you can have all that ahead of time. That's the part that doesn't change. That has nothing to do with our scenario. The battery, the switches, the NOT gates, they're always there. They have nothing to do with our scenario. The AND gates and this OR gate, that's where our scenario comes in. I'm telling you again how to cheat. I'm always telling you how to cheat in this class. You're going to have to build one of these. You can have 50% of it built ahead of time, ready to go. Come in, have it built. I see you building this from scratch. You're going to be wasting your time. I'm going to slap myself in the forehead or laugh my evil laugh, one or the other, depends on the mood I'm in. And but don't do that. You can have this much built ahead of time, and that has nothing to do with the scenario. It takes a lot of time to make it ahead of time. Now let's do the scenario. What was the scenario? This guy up here, this first guy was I hope I got it right. A, B, C prime. That was this third one. Is that all right? I connected to the A, I connected to the B, I connected to the C prime. That was one of my terms. This second AND gate, I'm connected to A, B prime, and C. That's here. This third AND gate going down was A prime, B, C. That was this first guy. And then this guy down here was A and B and C. That's the last guy. So I didn't build them in the right order, but they're all there. The order doesn't matter, just that they're all there and all connected. You have to do this on a lab. You have to do this on a test. Do you understand what I'm talking about? Do you need me to say it again? He says no. You can also get me to say it again by listening back to this recording.
It's just not the same.
And then I take the output of my AND gates and I put them into an OR gate. So these are those products, and then this is the pluses between them. Are we okay? Okay, or listen back.
Where is the output out?
What's that?
What's like, where is the output, like, where is that come out?
The output is the output of the OR gate is the overall output, and I have thrown it into a probe, which is under indicators. The other possibility I could do is put it to a voltmeter and connect the bottom of the voltmeter to my ground. So this probe is going to, it's not a real thing. It's like a fake, just a fake thing for the purposes of the circuit. And if it lights up, it's true, it's high, and if it doesn't light up, okay. When you grab a probe, let's see if I can do this, in multisim. Multisim. All right, so where are these things? If I made you build this, you saw last week, and you also, if you watched my video, here's the battery and the branch to that. So those things were under sources. Here's the one trick. Close that. I can come out of the battery and double click. So I can connect to nothing by double clicking. I can also place a node, place a junction. That's another way to do it. Place junction and then drag from the junction to there. Okay. What other tricks do we need to know? We need to know a switch. I think a switch is under basic. Here's a switch. There's lots of switches. I usually do the SPDT. And then the end with the twos, the side with twos was pointing up in my picture. The two side was pointing up and the one was pointing down of my switch. So I need to rotate it counterclockwise. If you're dyslexic and you get it wrong, you just do it 3 times, or you go back, or whatever the hell it is. Okay. What else? All the logic gates are under digital, miscellaneous digital, or I just used to call it digital. And then there's all these crazy numbers. Let's make life easy. Let's hit TTL, and then there are AND gates. There are like NOT gates. Let's do a NOT gate. They're in alphabetical order, so I have all these NORs, and then I have a NOT. So there's my triangle. My AND gates were 3 input AND gates, so I need 3 input AND gates. I needed a 4 input OR gate to make this guy, so I needed an OR 4. Don't grab a NOR, you want an OR. And then the last thing, what you're actually finally asking me about was a probe. So under indicator, they're the same place, they're like a voltmeter. So they're the same place as voltmeter, they're under indicators. And you have these probes. It chooses this top one for you. Never take that one. That one, whether it's high or low, depends on these little strokes. Pick me a nice color, so much easier to see whether it's on or off, if it's filling in the color. You can pick your favorite color, you can change them, you can have a whole rainbow. But that's much easier to see what's going on. So those are all the components that you see here in this logic circuit. You see the battery and the ground to establish your high and your low. The switches, so you can control whether the various inputs are high or low. The NOT gates, because sometimes the expression you're writing has not A, but A prime. The AND gates, because we're writing these product expressions. So the product corresponds to an and then ultimately you throw them all into an OR gate. That's the sum. So here's one product, and here's how I get the sum of products. Questions, anything? All right. So I switched to A was high and C was high, but B is low. So that's majority rule. So that should, and there's my probe lighting up. Here's just a different example. So a different scenario. The ABC part is all the same. The output part changes. That's a different scenario. In this approach, you focus on the ones. And you write an expression. It's a product expression. It's an and. You want everything that's going into the and to be a 1. So A prime, B prime, C prime. That's that first row. A prime, B, C prime. That's this one. This one down here is A, B prime, C. This last one is A, B, C. You only focus on you focus on the rows that have outputs of 1. That's the part that changes from scenario to scenario. The outputs change from scenario to scenario. You find the 1, you write the expression, the product expression for the ones. You want an and or a product expression. You want everything that's coming in here to be a 1. So if you see a 0, you prime it. A prime, B prime, C prime. Then finally, when you get all your expressions, you sum them or you OR them. Okay. So again, that's the sum of products. That's the minterm expression. That is on the lab. That is on the test when we have it. All right. We need 5-10 minute break or carry on, or what do you want? Nobody's saying anything. I guess you can, because you have stamina. I'll try to have stamina. Okay, let's do a purposely hard one. Here is a scenario. There are a lot of ones, so there are a lot of terms. So this is A prime, B prime, C, A prime, B, C prime, A prime, B, C. So there it is. 7 terms. But it's just an OR gate. Remember, our logic of the OR gate was if everybody's low, you get a low. That's the logic of an OR gate. The logic of the AND gate was if everybody's high, you get a high. The logic of an OR gate is if everybody's low, you get a low. So this is just an OR gate. This is a 3-input OR gate. So I can write it this way with these crazy 7 terms, or I can write it this way. I'd rather write it that way. Okay, so there's other approaches. I said that it wasn't unique. So here's a case where I can write the 2, at least 2, write it in 2 ways, and we can see they're logically the same, but they're not the same in terms of simplicity. Okay. Let's turn this boat around and come up with another way to express truth tables that is based on the zeros rather than based on the ones. So we are going to make now what's called the product of sums. Before we had the sum of products, we made products, and then we had a sum of them. Now we're going to do it the other way around. We're going to make a sum, and we're going to have a product of them. That'll be fun. Okay. So each row has an expression that is an OR expression, and that's 0 for that row and 1 every place else. When you want an OR, I want everything coming into my OR to be a 0. That's the unique thing for an OR, is when everything coming into it is a 0, you get a 0. So the OR expression for this first row is it wants zeros, ORs want zeros. I'll say 1, whatever the hell that means, but I'll say ORs want 0, and so that's and it's got its 0, so that's A plus B plus C, A or B or C. This next one will be A plus B plus C prime. It wants all zeros, the C is a 1, so I prime it, etc. So these are the ORed expressions. Is what we did before wrong? No. We can always do what we did before. It's always right. It always works. It's just sometimes it's not the best way. When you have lots of 1s and only a few zeros, this approach is better. So you sort of count up, are there a lot of 1s or are there a lot of zeros? Okay, so this is just the expressions. This isn't the truth table. This is just the expressions. But now we're expressing zeros. So in this new approach, you focus on the outputs, which are zeros, and write their expressions. So I'm going to only write expressions for these zeros in my scenario. And again, an OR wants all zeros. So this OR will be A plus B plus C prime. This guy will be A plus B prime plus C prime. A prime plus B plus C. A prime plus B prime plus C. And then you make a product of those things. So that is the product of sums or the max term. If I say make a truth table, I will sometimes say I want the min term. Or I might say I want the max term. If I just say I want an expression, then you can give me either. And you only, next week we learn how to simplify, and you only have to simplify if I say so. If you want to simplify, And I don't say that you have to, you're allowed to simplify. But I'm not, don't go through the extra work of simplifying if I didn't ask for it. So now here's the expression for it. The battery's the same. The switches are the same. The knots are the same. Again, 50% of that circuit that you could make ahead of time before, you can make ahead of time again. It's the same circuit because it's just all the possibilities. The battery, the ground, the switches, the knots, they're just sort of corresponding to the possibilities of things. Then we have OR gates, those are the sums, and then ultimately you have a product. So that is this other approach, this other way of building it. Questions? Are we all right?
How do you tell if it connects to higher low again?
How, say,
How do you tell if it connects to the higher low?
Okay.
again?
so right now, my A, I have this switch. And the switch is connected. The switch can flip back and forth. Right now, the switch is connected to the high end of the battery. That makes it high, that makes it true, that makes it 1.
Okay,
And if I were to type an A, or if I were to come with my mouse and flip the switch, this is just a picture, I can't do it, then I'd be connected to the low. So it's all about connections. Some people, like, right now I have this, the switches sort of going down vertically. Sometimes I'll make the battery sort of go vertically and the switches go horizontally. And then some people will think if the switch is angled up, oh, that's high. And if it's angled down, that's low. But it's, electronics is always about how it's connected. So is it connected to the high? Is it connected to the high part of the battery, or is it connected to the low part of the battery? It's always connections, connections, connections. I like to use and you can see it here, I did it. I like to change the color. I think the red is the natural color. I came in here and I right-clicked on the line and I can change the net color. And so then everything that connects to that line turns black. And so I tend to make my grounder line black. And then I'll see, is my switch connected to the red or the black? So, but the real thing is the connection. The switch A connects to the red, which connects to the high end of the battery. And these things are junctions. Sometimes I refer to them as nodes. And you got to make sure if you, sometimes you can have a node that's close to the wire, but not connecting, depending on how you made it. If you do this color changing, all those red things should change. So if I change the red to orange or something like that, it should all change. And that will indicate to me that multi-sim understands that they're connected. If they don't all change, then I probably rewire it. And the rewiring, it has to be off. So I can't be rewiring it while it's running. Questions? I'm going to have one of these on the test. You're going to have one of those, you're going to have one of these. Okay, this is just a synopsis of the expressions. So it is, just remember what you want to make. When you're working with ands, you want to make a 1. When you're working with the, you want to make, am I echoing? Keep that person, okay. So when you are doing the midterm, when you're working with ands, you want to make a 1 for the expression. And so if you see a 0, you should prime it. If you're working with a max term, if you're working with the sum expressions, then if you're working with the ors, then you want all zeros. And so then you leave the zeros as they are. If it were a 1, you would prime it. If you're thinking about that, if you have that logic in your head and don't do it too fast, you're fine. If you try to do it too fast, you'll get your primes wrong, because there are these two ways, and they're sort of the opposite. Okay. Switching topic to resistor. Anybody again? Possible place for a break. You're all Iron Men or something, I don't know. Iron Women. Okay. V equals IR, Ohm's law. So we sort of did all the basics last week, but V is the voltage, and it's sort of an energy per charge. So I'll often talk about sort of the charge having some energy when it leaves the battery and having no energy left when it gets back to the other side of the battery. The I is the current. I sit in one spot and see how many charges go by me per unit time. So how many charges go by in a second. And the resistance is the sort of the difficulty encountered. So is it hard for these charges to move through the circuit or not? The circuit is the same sort of origin as the word circle, and implies that there's some closed path so that they can move all the way around. If there's not a closed path, then it's said to be open or broken. So if somebody is troubleshooting a line, they will be looking for an open. Why isn't this path working? Why isn't it a circuit? There doesn't have to be one path. There can be multiple paths. So there has to be at least one path for it to be a circuit. Okay. So if I had an open circuit, I don't get any action. The light bulb doesn't light. If I have a closed circuit, then the light lights. Okay. So the analogy is that in the battery, as you're leaving the battery, it's you've had a good night's sleep, you've had a nice breakfast, you're full of energy, and then you're going to go out and carry out the tasks of the day. And then you are just going to expend all your energy and then fall into bed at night. So you're going to use up all your energy. So when you go around the circuit, you leave the one side of the battery with your, I don't know, 9 volts or whatever it is, whatever size battery it was, you have the 9 volts. That's each charge has some amount of energy per charge, but I'll talk about it. So it has some energy, and it's going to use that energy by the time it gets back to the other side of the battery. The charge has to get back to the other side of the battery, or the battery will get charged, and that always, to become charged, always takes up like more energy than not. So we have charges leaving the battery but coming back into the battery. So overall the battery was neutral and stays neutral. It's just the charges rearranged. They went out the top and they came in the bottom, and that allowed for some rearrangement that couldn't happen internally. Okay, so you're going to use up your energy. You're going to look out at the tasks that you have to do as you make your path through your day. And so if you have several tasks to do, then this is like resistors in series. And so you're going to sort of look ahead and divvy up your energy depending on the task. So I hope you saved enough energy for this class. Not falling asleep halfway through my class. All right. So that is part of the analogy. You're going to use up all your energy. You've got to divvy up your energy between your tasks if your tasks are in series, if you must pass through several resistors. So it takes a harder task, takes more of your energy. So there's more voltage drop across a higher resistance. So I have some battery, I have two resistors, they're in series. I'm going to use up, as I go around, my full voltage. I'm going to use up some of my voltage on R1, some of my voltage in R2. If R1 is bigger, then I'm going to use up more in there. If R2 is bigger, I'll use more there. And each one will have, so there'll be some voltage level here, but I'll often talk about the voltage across or the voltage drop. So I'll usually be talking about the change of voltage across R1 or the change of voltage across R2. Okay. So the two resistors are in series. If the current, so our definition of series is if the current that went through one must go through the other. So the charge leaves the battery, it went through one, it's got no place to go, it has to go through two. That is our definition of series. Sometimes we will have meters, and if we have meters set up as ideal meters, we're going to say that that doesn't change. So the meter is there to measure things, but not ideally to change them. So if I were to stick a meter in here across, say, the 2 kilo ohm resistor, I should believe that it doesn't change the circuit. I should imagine that no current is, no real amount of current is going through it, only the teeniest amount to do a measurement. Okay. Each resistor is each resistor is a resistor and obeys Ohm's law. So I can say, I can break down my circuit into little Ohm's laws. V1 equals I1 times R1. V2 equals I2 times R2. But our definition of series was that any charge that went through one went through two. So I know that I1 is equal to I2. And I know that the voltages add up to the full voltage. So my overall voltage is V1 plus V2. I use some of my energy on the first one, the rest of my energy on the second one. So that the two voltages add up to my total voltage. Each voltage is I times R. Each one of them obeys Ohm's law. The current is the same for both of them. So I can factor, I have the current I1 and I2 are the same, and I can factor it out. And then I've left my parentheses are R1 plus R2. I can call R1 and R2 an equivalent resistance. I can say that those two resistors act like they were one resistor, where if the one equivalent resistor, it has a resistance that is the sum of the two component resistors. And so that is how we combine resistors in series. Resistors in series add, and you end up with a bigger resistance. You have two tasks, it's harder. You know that. If you have two classes today, it's harder than if you only have one class today. You need more energy for the bigger class, the 3-hour class, than for the 75-minute class. But if you have two classes, it's harder than just having one class. One class can be harder than the other one. You might have highly, I don't know. He's always harder than me, even if I'm 3 hours. Anyway, okay. So resistors in series add. The equivalent resistance is larger. They have the same current, and the voltage is between them adds up to the overall voltage, and the voltage across the bigger resistor is bigger because it takes more energy to do the bigger task. So here's a simulated circuit with resistors 2 kilo ohm and 1 kilo ohm in series. and I have the circuit with a 3 kilo ohm replacing those two, and it gives you the same effect, the same current for the same battery. So I didn't change the battery, it's 5 volts. I have an ammeter, the ammeter reading is the same. That's what we mean by equivalent resistance. And if you apply the same voltage, you will get the same current, whether you have the 2 or whether you have the 1 that is its equivalent. Are we okay? That's fun. All right. So by current, we mean that there is many charges going by. So NV equals IR. If the task is hard, if the resistance is big, if the task is hard, then the current will be small. Not as many charges will take on that task. Okay, not as many people will take the highly class, but it's hard. Okay, you know that. All right. He's smirking. He's going to go tell Highly everything. All right. All right. If you have more energy, if you have a big battery, if you have a lot of energy, then the current will be more people. If you give the people more energy, if they have a bigger battery, then more people will sort of take on the task. So if V is big, then you will have more charges willing to take on the job. Okay. Now we're going to move, that was resistors series. We're going to do resistors in parallel. So now we're going to have our choice of tasks. So we're going to have multiple paths. We're going to have one way or another way to move through the system. And what's the system? The system is the circuit from one end of the battery to the end of the battery, but there's going to be more than one path from the high end of the battery to the low end of the battery. So that's what we're going to mean by parallel. And then we are going to figure out what happens in that situation. Okay. So here is a drawing with 2 resistors in parallel. We will say that 2 resistors are in parallel if there's a wire on the top, or there won't always be the top. If there is a wire connection on one side and a wire connection on the other side, then those 2 resistors are said to be in parallel. So you look for the wire on one side and the wire on the other side. That wire will be, or can be, or will be connected to other things. But there's a wire here. A voltage doesn't change along a wire. So the voltage drop is the same, because this wire has the same voltage as this wire, and this wire down here has the same voltage. So this R1 sees this difference, and R2 sees this difference, but it's the same difference, because this voltage is the same and that voltage is the same. That's how wires are. Okay, so this is our definition of resistors in parallel. If you see a connection wire, it doesn't mean in this picture they are like geometrically parallel. That does not matter. It has nothing to do with it. Electronics is about connections. If R2 were going up here, going horizontally up here, they would still be in parallel. It's about the connections. It's not about them being visually parallel. I will try to trick you someday and put it over here. If you understand that parallel in a circuit means there's a wire connection on one side, a wire connection on the other side, you will never be fooled. If I have a resistor just hanging there with its other end not connected, it's not part of the circuit at all, and you can just ignore it. I usually don't play that trick, but I had a professor who loved that trick. Okay. So here are 2 resistors in parallel. The 1 and the 2 are in parallel. There's a connection of wire on the top. There's a connection of wire on the bottom. Resistors in parallel see the same voltage. When you're back in series, they saw the same current, but parallel sees the same voltage. So the current comes out of the battery, it reaches this junction, and it has a decision to make. Do I want to go through the 1 or do I want to go through the 2? Some of them will choose to go through the 1, some of them will choose to go through the 2. More of them will choose to go through the 1 than to go through the 2 because the 1 is easier. But they don't like each other. They're charges. Charges don't like each other. Charges repel. So are they all going to go through the 1? No, because then they have to deal with each other and they don't like that. So it's not all the least, you can't just say what would one charge would like to go through the 1 kilo ohm because it's easier. So why don't they all do that? But they have each other to deal with. So some of them are going to go through 2, some of them are going to go through 1. More of them will go through 1 than through 2 because 1 is easier. But not all of them, because they also have to deal with each other. Okay. So here is resistors in parallel. Resistors in parallel see the same voltage. V1 is equal to V2. Their currents add. The current comes to the junction and splits up. And then when you get to the other junction, they add back up together. So the currents add. So the total current is the current that goes through the 1 plus the current that goes through the other one. Here's our game. We take that the total current is current through 1 plus the current through 2. Each one of them obeys Ohm's law. I is equal to V on R. So I replace each one with V on R, V on R, V on R. All the V's were the same. So put all the V's are the same, cancel them out. I can't cancel out a numerator and just have no numerator. If I cancel out a numerator and it's all gone, I put a 1 there. So I'm left with 1 over R equivalent is equal to 1 over R on is equal to 1 on R1 plus 1 on R2. This is how resistors in parallel add. They add reciprocally. The resistance goes down. If you play this game on a calculator, you will see that the numbers go down. It's always easy. If you have a choice, it's always easy. Resistors in parallel add reciprocally. The equivalent resistance is smaller, and it's always easier if you have a choice. So here is the 2 simulated circuits, the same battery, we have the same ammeter with the same reading, and here's the 2 and the 1. Okay. I'll show you the calculator thing. I do show you the calculator thing. Your calculator, any way you know how to do this, perfectly fine with me. And I'm sure there's some like resistance calculator out there on the internet, and you're allowed to use the internet on my tests. So if you've learned to do this, however way you've learned to do this is fine by me. I'm going to show you one way. Your calculator has a reciprocal button, and that's so use it. So I would do this if I were doing, what's my example? A resistor of 2.3 and 3.4, and I'm adding them. I would, in my calculator, put in a 2.3 and hit the reciprocal button, and then hit the plus. And then put in the second resistor, 3.4, and hit the reciprocal button and hit the equal. That will perform the addition, and then perform a third reciprocal. Our reciprocal formula, our parallel formula has 3 reciprocals in it. So if you're doing the calculation with the reciprocal button on your calculator, you expect to use the reciprocal button 3 times. You know another way, do it your way. I don't care, get it right. This way works, gets it right. Okay.
Can you show us an example?
Okay, what example do you want? Do you want the 2.3 one, or do you want me to go back to here with the 1 and the 2?
No, 2.3.
Okay. So,
I could do it.
okay. Oh, escape, I need to escape. And here's my calculator. A scientist has a 1 on. Does a standard have a 1 on? No. Oh, it does. Okay, so I can either be standard or I can be scientific. You want to be standard or you want to be
Standard,
scientific?
fine.
Standard's
Yeah.
fine, okay. And I'm putting in 2.3, my first resistor. And I'm going to hit the 1 on button. And then I'm going to add to that. And then I'm going to put in the 3.4. And I'm going to hit, and I want a reciprocal of that. And you can see up here, it's writing it out for you. 1 divided by 2, 3, okay. And did I hit the equal? No, it's lathered on, I don't know if I hit the equal. So I'm gonna do it again and not lather on so much. 2.3 reciprocal plus 3.4 reciprocal. I haven't performed the addition yet. So perform the addition with the equal.
Right, thank you.
And then 1 more reciprocal.
Thank you.
And I get the 1.37.
So you hit that reciprocal by essentially 3 times.
3 times. And you can see it in the equation, there were 3. There's 1, 2, 3 reciprocals. So I did put in a number, hit the reciprocal, hit plus. Put in the number, put in the reciprocal, put in the equal, put in the reciprocal. But if you know another way, oh, I should, you know, it's the multiplication divided by the sum or something like that. If you know another way, fine, use it. This is like my way, a way, it works. Okay. Okay. And then I already said to some extent, but I also always like to say, you know, when you have your choice, why doesn't everybody make the same one easier choice? And I've already sort of said, but I'm saying it again here. But this time I'm saying it before I talked about the actual charges and they don't like each other. Here I'm just using an analogy. Even in an analogy, if there's 2 ways to do it, it's always better than just everybody doing the one way. Okay, so we're in a theater, a crowded theater. You have freedom of speech, but you can't yell fire in a theater, but let's say you did anyway. And so everybody's got to get out of the theater. And there's these big doors in the back that a lot of people can go through easily. So that's an easy resistance. And then there's like 1 little emergency side door on the side. And now everybody's got to get out. It's because, like, yeah, if it's a bad movie and nobody's there but you, then you go out the back door and you're the only one. But if there are a bunch of people, then there's this jam up at even the big doors because everybody's trying to get out because there's a fire. And then if there is this other option, then it's overall easier if some people take the other exit. So it's because it's the interaction of the people or the interaction of the charges. You know, they have to deal with the situation that there are other things. And it's not just purely the fact that like charges repel, but just the fact that, you know, everybody's got to move through the door. Everybody's got to move through the door in the theater. Everybody has to move. If there's multiple doors, it's going to be better than everybody through the door, even if it's the easier door. So if there's a choice, it's always easier. Okay. And we use these ideas in computing even beyond just the electronics of this that make the computer work, but you talk about parallel computing. So you talk about, can I break my job up and have different computers do it? You know, there's a related idea. We call that parallel in the same way you call it parallel in a circuit. So we have series, we have parallel. If the resistors are in series, see the same current, their voltages add up and the resistors add up. In parallel, the parallel resistors see the same voltage. It's their currents that add up, and the equivalent resistances add reciprocally. Okay, so we have this idea there used to be, this is a very old picture of a very old computer, there used to be different ports in the back that were the serial port and the parallel port. And you say, well, that's really old and we don't do that anymore. But the thing that you plug into the side of your computer, that is a what? What if I were going to plug something in the side of my computer here, what would it be? A USB. And what's the S? Serial. Okay. We do more serial than we used to. But once you get down to the processor level, parallel. So there's still serial and parallel. There's not things you think in parallel move faster, and when you get down to the processor level, they do. So the processor works in parallel, but you have to coordinate things that are moving in parallel. You have to coordinate them to move in parallel. And so when as you get farther away from the processor, you move things in serial so that you don't have to coordinate as much. So we found out that we could go faster by being careless, doing it one at a time, but allowing ourselves to be careless. We could push it faster. So that's why most of our ports are now serial. But at the most internal part of the computer, it's parallel. So we still have parallel and serial in our computers. Okay. We have the meters, the voltmeter, since we're talking about serial and parallel. We will emphasize stuff we said last week. A voltmeter goes in parallel. Things in parallel see the same voltage. If you want to measure the voltage of something, you put your voltmeter in parallel with it so that the voltmeter is seeing the same voltage as the thing you want to measure the voltage of. Things in parallel have the same voltage, so voltmeters go in parallel. You stick the voltmeter in series, you burned up your voltmeter. Congratulations. If I walk by and start pretending that I'm smelling smoke, that means you've got your meters wrong and you need to fix it. But there won't be any actual smoke smell, but I'll pretend. Ammeters measure the current. Things in series see the same current. So if you want to measure current, you put your ammeter in series. Because things in series see the same current. So ammeters, because you want to measure the current, go in series. An ohm meter is a combination of the two, so you take it out because it's gonna have its own voltage supply and then measure the current for that voltage supply. So it's not going to, it doesn't want to be in the circuit to be an ohm meter. So here's my voltmeter in parallel. Here's my ammeter in series. Here's my ohm meter with nothing else, no batteries to be seen. Something doesn't work on the computer, well, then restart it. Yes, okay. Something hardware is wrong with the computer and you need to start checking things. So one of the easiest things to check are the cables. Do you have the connections you think you want? A cable should have a low resistance. So we can take our multimeter, we can turn it into an ohm meter, we can stick it on either end of our connector, and we should see a low resistance. Then we have a good wire, we have a good connection. When we're measuring connectivity, we're measuring resistance. When we measure resistance, we take it out of the circuit. So if we want to see if a connection is good, take the connection out of what it's connecting to and connect it to our multimeter set up as an ohm meter, and we should see a small resistance. An ohm meter often has a 1. If you're looking at a multimeter and you have a reading, it's over, it's, what is that, right justified. And sometimes it just shows a 1, but the 1 really means sort of like infinity on the other side. That is saying I have a high resistance, I have a bad connection. So you don't have to test anything more, it's the wire, it's the connection that was bad. I kept talking about energy being used. I had some energy at the one side of the battery and used up all my energy at the other side of the battery. Where did it go? Typically heat, sometimes light, sometimes it does something else. Maybe it lifts something, I don't know, but that energy, we have a concept in physics that energy is conserved. So that energy ought to really go somewhere. Typically in a circuit, it's heat. We have resistors don't do anything for us logically, but resistors are often in our logic circuits so that they can take it. They're tough, and the logic parts of our circuit are not tough. So the resistors are there to take the brunt of the current, so that we don't kill the logic part of our circuit. So sometimes that energy that we're wasting in a resistor is just wasted, and we try to minimize that so that we're not wasting too much energy to do our computing. And sometimes we want toast. I'm hungry, I could go for some toast. Okay. And that is me done blah, blah, blahing. I'm gonna hang out and let people work on labs. Is there any questions, anything you want me further to answer or demo while I'm still recording? You asked your lab 1 questions. Good.
I don't know if you need to demo this, but you have a question about the part C,
Part C of
the lab unit.
unit 1 or unit
Oh, unit 1.
unit 1?
It was that voltage current showing the unit.
Okay, I can talk about that
Oh,
on the recording still. Why
Okay.
not?
uh,
So in C, you're using multi-sim.
I built my circuit.
You built a circuit you're not asking about that. You built your circuit.
Yeah, no,
Okay.
specifically I figured out the voltage across R1, the current through R1, because your meters give that information when you change out your voltage. But the voltage current on the unit is the thing,
Okay,
and that's supposed to be I'm not
okay.
really sure what that.
So give me the first number here anyway.
I got 3.375
3.375.
and then 1.25 in it.
Okay. So then I don't divide so that I have my calculator
Oh, you
somewhere.
can, okay, that's what I.
You can use it, you can fill out all the numbers and use Excel.
Okay.
That's one way. You can just divide 3.375 divided by 1.25. That's 2.7.
Yeah, and then how do I know, is it voltage or current or is it like that's?
So then that's the number. Now I got to do the unit.
Okay.
So I have a volt. I have right now a volt divided by a milliamp. That's what I have right now. And that doesn't look like a divide. Okay. And that is a volt divided by 1,000 of an amp. And a volt divided by an amp is an ohm. So I have an ohm. And you don't have to do this every time. I just is my explanation, blah, blah, blah. So the volt over the amp was an ohm, and I still have the 1,000 in the denominator. No, I got one too many zeros in there. Dividing by 1,000 is like multiplying by 1,000.
Okay, okay.
Yes.
I'm sure it's there.
So I have 1,000 ohms, which is a kilo ohm. And then I could do a K, and if I'm really, really fancy, I could go insert symbol. You never need to do this for me, but there's a capital Omega, which is the ohm sign. Just saying, just spelling out ohms good enough for me, but okay. Showing you that I know Greek letters.
Show off.
Show off. And if the world is right, these should all be roughly 2.7. And the 2.7 was what you were measuring the resistance of. So what did you measure? You measured the resistance of the 2.7 kilo ohm resistance. So you,
Well, you have to tell me units within a, what is it, kilo?
kilo ohm.
Okay, let's see how you got, okay.
Yeah. And you should get 2.7 kilo ohms.
Yeah, I mean, it did, that's what it
So,
is.
so that's what it should be, and that's what makes sense in the world.
I love it.
So the voltage changed and the current changed, but the voltage over the current, the resistance should not change. Therefore, this thing is ohmic, and resistance is, a simple resistor is ohmic. And depending on how many decimal places you keep, it might be at 1.2.699999999.
Yeah, that's what I got. for one.
And yeah,
I've rounded up.
and don't tell me it changed.
All right, thank you very much.
Any other questions? I tell you, I will answer all your questions, just ask them. Anything else for the recording? All right, I'm gonna stop recording.